welcome back. You have made it to level 5 of Jumanji. I mean, day 3 of DevOps days. All right, y'all sound really tired. Can we all stand up for a second? I know, it sucks. You just ate. You're like, man, I want to take a nap. But this is not nap time. All right, for our next talk, we have Steve Hallman talking about how you can use queuing to your advantage. All right. A little jumping around? Yeah? Okay. You can sit back now. Thank you all for playing with me. Steve, are you ready?
I am ready.
All right, Steve Hallman, everyone.
Thank you, everybody. All right, making sure I know how to drive this thing. That gets me forward. That gets me backwards. Awesome. Okay, so I've talked to and introduced myself to a lot of you so far this week. I'm not a coder. I'm not an engineer. I do have some production code out there in the world, but you do not want me to solve your coding problems. What I do is process, basically. My name is Steve, and my world is process. So if you're interested in following up on anything, I very occasionally blog at the Agile Couch. That is my LinkedIn. I'm still on the thing I'm going to call Twitter, at Steve Twips there. So what I get really excited about is being able to increase productive throughput or business value or code quality without spending money or spending more money. In fact, I promote what I call radical team ownership, which is that a development team should own its own budget. So if they want to hire other people, then they need to figure out how they're going to allocate that money. But that also means that they get the rewards if they change the business model and increase productive value, increase the revenue or profit margin of the company. They should share in that joy as well. So I'm going to talk a little bit about science. If some of you were here for Monday afternoon's talk, we did this workshop and sort of showed that something as simple as writing a name on a card for a customer can vary greatly in time based on how you do it. The first round at the top there is doing it one at a time, right? The basic rules there are never keep a customer waiting. So you're always trying to keep 3 cards going. The second round is the exact same activity. We've just changed the rule where you can deal with 1 customer at a time. That costs nothing. It's free. And most companies are still living in this space. If you've got developers that have like 3 Jira tickets with their name on them in the middle of a board somewhere that's work in process, you're burning piles of money, and you're probably blaming it on developers. They could be doing this and putting things into production sooner and making you more money quicker. And it doesn't cost anything. You don't have to buy a software package for this. This I meant to show on Monday and I didn't, but this is a team which I worked with for a year, and we did that exact workshop. Had an extremely stubborn manager of the development team, and his background, his world was not in software at all. And so he was the ultimate example of trying to operate a software team as if it were a factory. And their past 2 years essentially looked like this. And this is when I started working with the team, and this is when we did that workshop. So I did that workshop, and I made that manager be one of the developers in that little exercise. And his quote, immediate reply when we finished was, "Holy shit. Can you come and do this same exercise at my manager's meeting and show it to all of them?" And at that point, we got buy-in from all of the customers of that software group to do things a little differently, and we increased that team's throughput by 1,600% in less than a year. So what I want to talk about today is a little bit about discrete event simulation We're going to use that as something to show you some proof of queuing theory. Queuing theory is all ruled by something called Little's Law that describes arrival times and working process and the completion time of an event. I'm not going to dive into the math. We're just going to look at how it works. We're going to see what it actually does. I don't think I'm going to need this. I was going to ask if I could get some people to enter data for me, but if you want to pull up this spreadsheet and follow along or make a copy of it for yourself, I think that QR code or the tiny arrow there will get you to it. But I think I've got good data. I don't think I'll have to change it. And if I do, I think it'll be slight and I can do it myself up here. So one of the core problems in trying to make anything more efficient is that you have to define what efficient means. I can come up with at least 10 different terms for efficiency, and the problem is that some of them converge and some of them are inverse. One type of efficiency is a hard trade-off to another. So as you increase the one, you're decreasing the other type of efficiency. That first exercise that we looked at there in round one is trying to optimize resource efficiency. In other words, I'm paying 9 developers to be here for 40 hours a week. I want to squeeze as much work out of them as I possibly can. If you approach it from that mindset, what you're doing is trying to fill an 8-lane highway full of cars bumper to bumper so that you're not wasting any highway. Resource efficiency is inverse to flow. And flow is what we want in a software environment. Idle time is not the worst thing that could happen to you. In fact, idle time is sometimes the best thing that you can do. You can have an engineer or a developer not doing something and that be the most productive thing for the entire system. So we're going to talk about these trade-offs in efficiency. And again, as I said, this is all sort of dictated by something called Little's Law. As you try to maximize resource efficiency, whether it's a machine or a person or a chunk of highway, as resource efficiency approaches 100%, the cycle time of producing any given thing approaches infinity and your flow approaches 0, right? So 100% resource utilization is a system where nothing is moving. All right, so I'm going to switch over to our flow simulation, and I'm going to show you what this is and what it does. There's a gentleman named Michel Grutjans who wrote this, and I was really intrigued by his little GitHub project, and then I started speaking with him about kind of modifying it, and this is where we've gotten it to. So the reason that someone would do discrete event simulation is when you need analysis of a complex system. So you have a very simple system like you have a dock, and once a day a truck pulls up to that dock and unloads things. You have plenty of idle time. So you can do very simple math and say, well, if I have a second truck come 12 hours later, I can double the amount of material I can receive in a day. That's simple because the two trucks are not impacting each other. When you have a dynamic system where the individual objects in the system interfere with each other, you then have to do what's called discrete event simulation. You can't just take a big number and multiply it by 2. You have to model each individual object as it moves through the system. And this is used for things like planning how people would leave a building in the event of a fire or an emergency. You actually can model thousands of people moving through a building. You can use it to plan how many forklifts do we need in a warehouse. You can do things like set up your Chick-fil-A drive-through with a complete digital simulation and then say, well, what would happen if we split people up to 2 different order boxes and then had them go to 2 different windows to pick up their thing? Well, what if we split them to order boxes but then converge them back to a single pickup window? You can model all those different things and then run 100,000 simulations in a short period of time, and you can see what the results are. The result isn't a single answer. The result is some distribution of data, usually. This is a very, very, very incredibly simple discrete event simulator. And it works like this. You have work per story, which is some ratio of the amount of time. You could think of this as 1 hour or 1 day or something like that. I'm just going to call it a day from here on out. You could define this position any way you want. This isn't code. It says dev there, but you could put painter or musician or whatever you wanted to. It just says dev because that's generally the place that this is getting used. And here we're defining how many workers we have. If I had 2 developers, for instance, I could just put in a comma and dev. I've got all of the teams that we're going to look at already pre-built, so all I have to do is copy and paste these things in. You've got a work in process limit, which at the moment we have none. You have number of stories or item objects, whatever you want to call it. They're going to move through the system. You can turn on variable work. Generally, this is meant to operate where one object is going to move through one person at 1 unit day, right, based on these ratios that you define. If you turn on variable work, it puts a little bit of jitter on the data. So rather than a 1 unit day, sometimes it'll be 0.9, sometimes it'll be 1.13, something like that. So you get a little bit more realistic behavior from the system as it gets complex and things move through it. And then what we're going to look for in outputs is throughput, how much stuff is moving through the system. Lead time, which is generally in an agile software environment, your lead time is the bigger measure of the time that someone comes up with an idea to the time that it's usable to a user in a production system. And your cycle time would be usually when you commit or start working on it to the time that it's, so cycle time is smaller and lead time. But in our case, it's kind of going to be the same thing. We're just going to refer to it as lead time. Then we'll see our work in progress. We'll see the time worked, how many unit days did it take to get the thing completed, and some statistics on the idleness or the resource efficiency of the people involved here. Okay. So to run a very simple one, if you do numbers, I think under 100, it will move very slowly, and you can see what happens here. So we have 1 developer. Our work ratio is it takes 1 unit day for the developer to produce something. We're going to produce 50 things. And I'm going to hit run, and then you can just see them slowly move through the process. So he has a backlog of 50 items that he starts with. He pulls and seizes 1 item. He seizes that item for 1 unit day, puts it in the done column. Then he picks up the next item. Your output from this simple of a model is going to be really straightforward. It's going to be really close to 1 as your throughput number. Just tapping the fingers, waiting for things to happen. When we go to a larger number, it moves a lot faster. We don't care to watch the things, but this is a good way to just get the visual idea of what it is that's happening here. All right, so we are finishing up our final statistics. Our throughput is like 0.99. That's exactly what we'd expect. Essentially takes the person 1 unit day in throughput. Our lead time is essentially 1 day. Our work in progress is 1 because we're only having 1 person work on 1 item at a time. And our time worked is going to be really close to 50 because we have 50 items. It takes 1 unit day to do them. I'm going to turn this up to 100 just to make it go faster. And then I'm going to switch on variable work, and I'm going to leave that on for the rest of them. You'll notice how the cumulative flow diagram and the flow metrics look super clean and easy because everything's a unit 1. When you put that variable work on it, puts a little jitter on the data, it's a little more realistic. So we'll use that for the rest of our simulations. So now it's going to run through 100 things really quickly. All right, and then we get slightly different data, right? Our throughput dropped a little bit. Why would our throughput drop? This is the interactive part.
You've only got 1 dev and you're moving variable amounts of work through the system at a time, so occasionally it's going to kick over where what used to take 1 day now takes 2.
Right, but then some of them are going to take less than a day, so why isn't it an average? You can't ever make up that lost time. If it takes you a unit day to do something, the less time does not help you in a complex system. Imagine a factory where you've got machines and You got to put part of a sandwich together here and then another part of the sandwich together here. If somebody gets done early, it doesn't do any good if it takes 10 minutes to bake the sandwich in the oven, right? So you have certain things that are fixed. You can only lose time. You can't ever make it up. That's a really important concept to keep in mind. All right, so again, our lead time, about the same. It's 1 on average. Our max lead time went up to 1.7. Work in process, still about 1. Time worked ends up being twice as long because of 2 things. We've changed 2 variables. We're doing twice as many pieces of work, and we've put some jitter on our data, okay? So our developer now is 92% resource efficient, okay? These numbers are gonna change a lot more with the team structures that we're about to plug into this, okay? So I'm gonna reset this to get a clean slate, and then we're gonna look at, I'm not gonna use that anymore. All right, so I've got all of these pre-built. So we're the banana software company, maybe you've heard of us. What we've got here is a work ratio where I just broke things down. Again, you could name these literally anything you want, but I just put them into, say, product owner, UI developer, back-end developer, QA, for instance. And then we have a base team of 8 people, so I've got 2 of each of those. Just gonna keep things as simple as possible. The work ratio is it takes a product owner about a day to talk to a customer, interview them, understand what they want, write up the specifications for the thing they're asking for. It's gonna take that front-end designer about 2 days to do his work. It's gonna take the back-end developer about 4 days to do their work, and about 2 days for a QA person to test it, okay? Again, these numbers could be anything. I just put something in where that they're different. You get a sense that there's some larger pieces of the work, some smaller pieces of the work, and we're mostly gonna keep that ratio the same until we get further in. We're gonna do 100 pieces of work, and I've already got my team topology built, so I'm just gonna copy that and paste that back over. I can't figure out, wait, I don't actually need to do that because I'm just going between tabs in a thing. There we go. So I'm just gonna plug my workers in here, okay? So we've got work per story I need to change. This is easier if I'm not full screen. All right, so here's our work ratio. I'm gonna go plug this in. Okay, PO, 1 day, UI, 2 days, dev, 4 days, QA, 2 days. 2 POs, 2 UI, 2 devs, 2 QA, no WIP limits. We're gonna do 100 items. We're always gonna use variable work. We're gonna run the simulation. So you'll notice at the bottom, now that we have more workstations, things are going to build up. You have a backlog building before you get to the back-end developer because it takes them 4 days to do something. So even though other people are doing work that takes 2 days or takes 1 day, then things are gonna back up because you have a disjunction in flow rates between these different pieces, right? So one of the things we're gonna notice here is when you're looking at resource efficiency, our back-end devs are gonna be very, very busy because they're the longest tent pole, and our QA is gonna be much less busy down here, so we've got 42% on that, okay? And I think my numbers here, maybe this is the better way to do this. Let's see if we do over under. Other way. All right, now we're having fun. Throughput 4.6, I had 4.5. Lead time 161. WIP 78, 77, close enough. Time worked 217, 220. I'll go ahead and change that. That's slightly different. All right, so now we have a base team. So now we're manager bros. We slept our way through college, and we just learned that, like, man, if there's a thing you can measure, you want like more of it, or if there's like another thing and it's cost, you want like less of it, right? And I don't like these developer guys. They just cause problems for me. And if we're developers that slept our way through code boot camp and we're constantly being pressured by this management bro, the one thing that developers and management seem to always find a way to agree on is we need to hire more people. So that's going to be our first attempt. We've got a team of 8 people that can do 100 items. The team size is 100% because it's our base team. Everything will get compared to that. Our throughput is 100% of itself because, again, this is our base rate that we're starting from. We're just going to assume everybody makes a flat 100K, so that makes the math easy. 8-person team. We got an $800,000 team for the year. Our team cost is 100%. Our throughput per expense is 100% because, again, this is our base model. Okay, so our management bro and our developers have decided we've got so much work to do, we need to double the size of the team. That's going to be our first attempt to get more software out the door. So the only thing I need to change here is our team topology. So I'm going to blank that out. We're still doing 100 items, still variable work. The work ratio hasn't changed. We're just introducing more people. So we run it. So what has changed? Our throughput has gone up. Let's see where we're at here. 89, 89, perfect. 84, 85.7, close enough. 81, 80, time worked, 113 days, 112 days. Pretty close. Okay, close enough. I'm not going to change those values. So our team size is now 200%. We have 16 people instead of 8 people, which means our team expense is 200%. We're now spending $1.6 million instead of $800K. Our lead time has decreased. That's fantastic. That's one of the things we want. When somebody asks me for a piece of software, I can now get it to them in close to half the time it would have taken before. 47% drop. That's pretty good, right? That's what we would want. Now, the problem is that throughput per expense is taking into account how much my throughput increased relative to how much my team cost increased. So that number is not double, it's 99%. What do you suppose is going to happen if we keep increasing our team size?
Got to reduce that number a little bit.
Yep. So in the interest of time, I will skip ahead and just tell you if we do 3 times the people, 4 times the people, 8 times the people, and we're changing nothing else, that number is just going to keep decreasing, right? Marginal throughput per expense. I'll go ahead and do the 8X team here and run it. All right, and I should have something close to 291, 292, that's good, 27, 27, whip max 100, time worked 34 days, good, yeah. So now we've got 64 people where we had 8. We're trying to buy our way to productivity. So our team size is up 800%. Our lead time has decreased massively, which is great. We can get more software out the door sooner. But our throughput per expense, you notice, is going from 99% to 94% to 92% to 81%. The more people that you add, that ratio is going to keep dropping off and dropping off and dropping off like that. You're going to get declining returns. It's also important to note that this is a stupid robot doing the most basic kind of discrete event simulation you can possibly do. If you actually take a team of 8 and you scale up to 16 or 32 or 64, you're introducing all kinds of communication problems, interpersonal friction, differences in knowledge base that we're not representing here. So this is the best that you're ever going to get. In real terms, it's worse than this, okay? All right, now we're going to start to get fancy. Instead of spending money, we're going to try the free toolbox. My buddy Steve told me there's all these free techniques that you can do, and you can improve your throughput without spending extra money. So let's reach into the free toolbox. So we're going to set our team back to our starting base team, okay? Gonna go back, rebuild my team topology, 8 people, okay? We are now gonna be throttling work in progress. We're gonna say we're gonna have no more than 8 tickets in the system at a time. We could tweak this number. We could go up and try like 9, 10. We could try 7, 6, see what the difference in output is. But a safe place to start for work in process is just the number of people that you have, or maybe half the number of people that you have are good places to start. So that's the only difference. We're back to our base system, 8 people, same skills. The work ratio has not changed. We're just going to limit the number of objects that we allow into the system at a given time and compare that to our original team performance. Chugga, chugga, chugga. All right, and we win. And how close are we here? 46, 16.9, max 20.6. I'll change that one. Let's make that 20.6. Whip max 9, that's good. Days, time work, 2016, 217, close enough. So we've got 8 people. We're still spending $800K on the team. Our throughput went up by 2%. Just by having less work in the system. Our throughput went up by 2%. Our lead time dropped 87%. It used to take me 161 days max lead time to get an idea into a user's hands. Now it takes me 20 days. That's a profound difference. Now, what's the trade-off? If my lead time is dropped, why isn't everybody doing this all the time? Somebody in that backlog is at the back of the line. If you're only allowing 8 units of work into the system at a time, now you have to prioritize. So if you're trying to serve 73 different managers and everyone says everything's number 1, they're not helping themselves, they're not helping you. You have to establish a rank of business value of the work that you're producing. But as long as you can do that, you're winning. I came up with this crazy idea in my head one day that trying to make everything number 1 is like a bunch of cavemen trying to kill a mammoth by pressing a sheet of plywood into it, right? You have a blunt object. In order for something to make progress, it has to be pointy. If you have a bunch of cavemen holding a spear and you've got 1 point, you've got 1 ticket that you know is the most important thing that you can do, you're crushing it, right? All right, I'm gonna skip down here. This is what you get if you do the other tools, cross-skilling. What you're doing in this case is I've got people that can each do 2 of those skills, right? Cross-skilling cuts your lead time, increases throughput, still the same team cost. Third free tool, cutting batch sizes. If you cut your batch sizes in half, we then have to do 200 units to get the same amount of work, but we're cutting the amount of work that we're doing in half. And usually all of your work doesn't get cut in half. So I would model that by doing something like saying the 1-day work of the product owner is still probably going to be 1 day, but the things that are 2-day work are now going to be 1. The things that are 4 days of work are now going to be 2. You'll end up with throughput per expense in the 196 range. If you then start combining those, you do some whip throttling with cross-skilling, with cutting batch sizes, your throughput is in the 273% range. Your throughput per expense, again, 273% because you haven't changed any costs of actually running the team. And then you can kind of like cheat it by just putting in full stack and it will run as if any person on that team can do any of those roles at any time that they're available. So in order to get something like 273% or 302% increase in throughput by spending money, you'd have to increase your team size somewhere in the 2.5 to 2.6 range, right? You'd be doubling the cost of your team. So, as I said, you can't simply optimize efficiency because there's different types of efficiency and they are offset from each other. Whip throttling is free, cross-skilling is free, cutting batch sizes is free, adding people's expensive. There's about 28 things I've got on a list of the free toolbox. Any one of these given things could probably double your throughput by itself. That doesn't mean that if you do all of these, you're going to keep doubling and doubling. But all of these can give you some significant results. So love talking about it. If you'd like to see what some of these practices are, this is a tool that I've built. It gives you things from 1984 to like 2022. And you can you can audit which of these technical practices are we putting into use. And wherever you stop there, if the last one you've adopted is in 2003, then your software organization is essentially operating in 2003. And it gives you a way to find the things in here that are free toolbox tools that you can apply and increase your throughput, code quality, and business value without spending any extra money. And I'll wrap it up.
Big round of applause for Steve. Thank you.